More math, segment 3 of gases. So we did Boyle's law, Charles' law, Gay-Lussac's law, and then I started explaining how we're going to put them together to form what we call the combined gas law. So it's basically all three of these together. P1 V1 over T1 is equal to P2 V2 over T2. This pretty much lets us figure out any changes that are made in the gas, as long as we hold one thing constant typically, right? So in this case, we'll be thinking that the mole, the amount of gas that's there, is what's going to be the constant. We can rewrite this again. So we have P1 V1 T2 is equal to P2 V2 T1. That might be a little more useful. However, that's up to you, right? You can leave it as P1 V1 over T1 if you'd like. So an example, 15-liter cylinder of gas at 4.8 atmosphere pressure at 25 degrees C, lots of information in here, is heated to 75 degrees C, then compressed to 17 atmospheres. What is the new volume? So now we're going to change the temperature, we're going to change the pressure, and we're going to see what the impact is on volume. So again, we'll do something like P1 V1 T2 is equal to P2 V2 T1. Now, just like before, our temperatures need to be in Kelvin. So that's going to be 298 K. 75 is going to be 348 K. All right. Now we're ready to plug and chug. So a 15 liter, we're going to let that be V1. Gas, 4.8 atmospheres at 25 degrees C. Those are all my ones. All right, so that's going to be V1. That's going to be P1. This is going to be T1. Is heated. It's going to be T2. And then compressed to P2. We want to know what's V2. So V2 is going to be equal to P1 V1 T2 divided by P2 T1. And now we've got everything labeled up in here in the question. So P1 we said was going to be 4.8 atmospheres. We're going to multiply that by V1, which we said was 15 liters. We're going to multiply that by T2, which we said was 348 K. Then we're going to divide all of that mess by P2, which is 17 atmospheres, times T1, which is 298 K. All right, atmospheres cancels out. Kelvin cancels out. We'll be left in liters, so that's looking pretty good. All right, so we're going to take 4.8 times 15 times 348 divided by 17 divided by 298. We're left with 4 point, how many sig figs? That's right, 2. 4.9 liters. Final answer. All right. Hopefully you were able to knock that out of the park. So let's look at another one. If 6.2 liters of gas at 723 millimeters of mercury at 21 degrees C is compressed to 2.2 liters at 4,117 millimeters of mercury, what is the temperature of the gas? And again, I want that in degrees C. But we have to do the work in Kelvin. All right, so pause your video, give it a shot. Before you pause, remember it's going to be P1 V1 T2 is going to be equal to P2 V2 T1. And again, I would pause right about here. All right, hopefully you've come back to the video, you've hit play, and now you're going to see how you did. So 21 degrees C, hopefully remember this has to go to Kelvin. 273 plus 21 is going to be 294 Kelvin. Let's see, so now we got 6.2 liters. We're going to let that be V1, 723 millimeters of gas. That's going to be P1 and then T1. And we're going to compress it to P2. Whoops. And we're going to compress it to V2. It's liters, caro, liters. And then P2. All right. I want to solve for T2. T2 is going to equal P2, V2, T1 over P1, V1. Plug and chug. P2, 4,117 millimeters of mercury times V2, 2.2 liters times 294 Kelvin, T1. I'm going to divide all that mess by P1, 723 millimeters mercury times V1, 6.2 liters. Liters cancels out. Millimeters of mercury cancels out. I'll be left in Kelvin. So T2 is going to be equal to 4,117 times 2.2 times 294 divided by 723 divided by 6.2. And that gives me 594. However, I only get two sig figs, so 590 Kelvin. But we want it in degrees C. So 590 minus 273, 320 degrees C. Final answer. And of course, my calculator gave me 317, but you have to stop at the tens place because the 590 stops in the tens place. All right, so that was using the combined gas law. Now, the combined gas law gives you all the other gas laws. Now, typically back in the elder days before coronavirus, and I went to videos, of course, on exams, being online, the whole 9 yards here, you can pretty much use whatever you want. But in the previous courses, I only gave them the combined gas law. So I would suggest you get ready for that just in case. You can always pull this out, and it just gives you a better understanding of gas laws in general. So all three of these variables are going to be in there for every gas. It's just a matter of which one are we holding constant. For instance, if we hold the temperature constant, we know that T1 will be equal to T2. They go away. What's left over? P1 V1 is equal to P2 V2. That's Boyle's law. All right. And that's what we started out with Boyle's law. We said if the temperature remains constant. Okay. What about when the pressure remains constant? Well, that means we're going to make P1 go away and P2 go away because they're equal to one another. And lo and behold, we have Charles' law. And that's exactly what Charles' law said. It said when the pressure remains constant. Finally, we've got that whole volume, right? If the volume remains constant, V1 is equal to V2. And now we're left with Gay-Lussac's law. Okay. Now remember I told you there were 4 variables. The one variable we've not taken into account yet has been the mole. That's right, your friend the mole. The 4th part has to do with Avogadro's hypothesis. And of course, the minute we hear avocado or Avogadro, we start thinking the mole. V is proportional to the number of molecules. So volume and the number of particles are proportional as long as temperature and pressure are constant. So V is proportional to moles. We can then do that kappa thing again. However, I don't want to do the kappa thing again. I'm actually going to take this, plug it back into the combined gas law, and what drops out is what we call the ideal gas law. Now, don't worry about all the manipulations to get there. It's not important. This is just a second equation that you need to know. So we have combined gas law, and then we have the ideal gas law. Now, the ideal gas law is also referred to as PV-NRT, right? PV-NRT. PV equals nRT. So P, V, and T, we all know those. That's pressure, volume, temperature. No big deal there. However, you now have the number of moles. And so N is the number of moles. And then there's this R. Well, R is actually like kappa. It's a constant, except this time it's a real constant. And the real constant then really does have a value. So this time R does not depend on anything. It really is a constant. We're not going to flip things around and plug it back in. We're going to have some values for R that we're going to need to have handy. So the first value you want to have handy is going to be 0.0821. And look at this unit. This unit is insane. Liters, atmospheres per mole Kelvin. Liters, atmospheres per mole Kelvin. So it's liters times atmospheres divided by mole times Kelvin, right? So 4 units in this complex unit. Now, remember, some of these things can change and some of these can't. So that's going to give us different R values. In fact, if you got onto Google right now and Googled gas constant R, it'll give you a list of R values. Don't do that, but if you want to for fun, you can. Now, why do we have this long list of R's? Well, remember, we don't have to work in liters, but in Chem 110, Chem 110 and 100, we do. We work only in liters for the most part. Maybe milliliters, but that's just liters, but different, right? Then we have the pressure. Well, we did say we're going to work with 2 different pressures. We have atmospheres and we have millimeters of mercury. So this value is good for atmospheres and liters. Now, moles in Kelvin, we're not going to change too much, right? This is the absolute scale Kelvin. And so just like we did all of our gas law equations in Kelvin, we'll continue to do it in Kelvin, right? And of course, the mole is the mole. We can't do anything about that. So if we change our pressure, then we can end up with another value. And so if I change that pressure to millimeters of mercury, we get 62.4. Now notice it's still liters, but now it's millimeters of mercury per mole Kelvin. Okay, and again, here I have Kelvin mole. It doesn't matter. They're both on the denominator. That's all that matters. Now, the key here is we now have a way to count moles by using gases. So we're not going to be restricted to what's called STP. Now that matters more for 110 than 100. And that's because stoichiometry is going to come back to get us. That'll be probably part 4, segment 4 of the series. So we'll cut where 100 can stop here. Now, to figure out moles, we'll rearrange so that we get PV over RT. Okay, PV over RT. So what are some example problems? Well, how many moles of air are there in a 2-liter bottle at 19 degrees C and 747 millimeters of mercury? So again, as long as we know our R values, we can look those up and it's no big deal. So we're going to have PIV inert, PV equals nRT. And then we're going to start plugging and chugging, right? How many moles? We're looking for moles. So N is going to be equal to PV over RT. They tell us the pressure is 747 millimeters of mercury. We're going to multiply that by volume, which we're told is 2 liters. We're going to divide that by R. Now here's the key. Which R do I want to use? Well, since we're in millimeters of mercury, I want to use that 62.4 right there. So we're going to put that in. 62.4. Of course, that's millimeters, mercury, liters, moles, Kelvin. I promise you all those units are there, even if they're microscopic. Times T. Now T also has to be in Kelvin now, so we have 19 degrees C plus 273. It's going to give us 292 Kelvin. Now we can see Kelvin's going to cancel out. Liters is going to cancel out. Millimeters of mercury is going to cancel out. We'll be left with moles. So that means we're on the right track. Get our handy dandy calculator out here. We've got 747 times 2 divided by 62.4 divided by 292. And that gives us 0.0819942. How many sig figs do we get? Dose, all right, 2.0. And so that's going to be 8.2. And the unit, of course, will be mole. All right. Good to go, I hope. Let's take a look at another example. What is the pressure exerted by 1.8 grams of hydrogen in a 4.3 liter balloon at 27 degrees C. And so there it is. We have grams. We don't need grams though, right? We need moles. So how do we get to moles? That's right. We'll use our periodic table. So the first thing we'll do is take that 1.8 grams and I want to convert that to moles. And we know that 1 mole of H2 will have a mass of 2.02 grams. And that's coming from the periodic table. That's not in the question, right? That's the periodic table. Coming back to haunt us, 1.8 divided by 2.02. So we have then 0.89 moles of H2. Now we want to know what the pressure is. So PV equals nRT, piv nert. We're looking for pressure, so that means pressure would be equal to nRT over V. Now it doesn't tell us what the unit of pressure is going to be here, but because we used the 62.4 on the first problem, I want to let this be atmospheres, so comma, atmospheres, because that way we can use the other R value, right? Gives a little bit of practice with each one. So for moles then, I'm going to plug in the 0.89 we just calculated. I want to multiply that by that R. You can flip back a few slides if you need to. And it's 0.0821. 0.0821. That's atmospheres, liters, moles, Kelvin. And we need that Kelvin temperature again. 27 plus 273 is going to give me an even 300. And finally, we're going to divide that by the volume, which we're told is 4.3 liters. And so pressure then in atmospheres will be 0.89 times 0.0821 times 300 divided by 4.3 gives us 5.1 atmospheres. And hopefully we did everything right there. All right, so for Chem 100, you're done gases. For Chem 110, this will end the segment, and then we'll do our last segment on stoichiometry with gases. And so if you want to, in the meantime, before you do the next segment, you might want to go back and review the stoichiometry, just to remember there's 3 steps. We're going to go from mass to mole, mole to mole, mole to mass. The mole to mole piece will stay the same. We saw that in the middle of stoichiometry. That remains a constant. If you have that mole calculation flow chart, remember you're going to be using the wings of that. So now we have a gas law side and we have a solution side. So this will be the gas law side for you. So you might want to get some of those papers out, get them ready. You'll be needing those in the next segment. All right, enjoy.